Good day, everyone. So today we shall be looking at electromagnetic field. Electromagnetic field. So without much ado, let's dive into this topic. When we talk about electromagnetic field, it's actually a combination of two words, electricity and magnetic field. The combination of electric field and magnetic field. Now, electromagnetic field is a field arising from the combination or combined interaction of these two fields, magnetic field and electric field. And how can we verify this? Very simple. You get a cardboard and make a hole at the center of the cardboard. Pour some iron fillings on that cardboard as shown in this diagram here. Then you get a wire, electric wire that we call the straight conductor. Insert it in the hole of that cardboard and connect the wire to the source of electricity like battery. When you do that, you will observe that the iron fillings on the cardboard will come around the wire and form a kind of concentric circle around the wire. And that formation of concentric circle shows the direction of the magnetic field. Because for an iron filling to be attracted, that means there is a magnetic property. And this next diagram here shows the direction of the magnetic field. So this arrow here points to the direction of the flow of current coming from the source of electricity like the battery here. So that red arrow shows the direction of the current. Now the green arrows moving around show the direction of the magnetic field. So the combination of the electric current that produces the electric field is called the electromagnetic field. All right. So let's go further to study some concepts in this observation. Now that will take us to magnetic field around a circular conductor carrying current. Of course, in our previous slide, we could see that magnetic field was generated as a result of what? This conductor carrying a current. Now, how do we now know the direction of the magnetic field? Although this previous diagram has shown us the direction. But then, two scientists propounded law that guided, or rule rather, that guided the direction of the current and also the direction of the magnetic field. And the first was propounded by Clench. His rule was known as right hand grip rule or clenched fist rule. Now let's take a look at this rule. In this rule, it said that with the right hand being fist in a way that the thumb, you could see the thumb point in the direction of the flow of current, and the finger, the guide of the finger point in the direction of the magnetic field. As you can see, the fist is made in a way that the thumb is pointing the flow of the direction of the current, and the rest of the four fingers is pointing in the direction of the magnetic field. This is what we call the right hand fist rule. The second rule is known as the Maxwell corkscrew rule. You know what a corkscrew is, and we use it to open drinks. Now in this rule, he's saying that when you get a corkscrew, as shown in this video, the direction of the corkscrew tells us the direction of the current, and then the rotation of the corkscrew shows us the direction of the magnetic field. So these are the two rules that guides the direction of magnetic field and also the direction of the flow of current in an electromagnetic field. All right, having said that, let's talk about what if we have two wires or two conductors that are parallel to each other, as shown in this diagram here. Two conductors parallel to each other, one on the left and the other one on the right. Okay, by the time you do that and you connect the two of them to electricity, now they are not carrying current in the same direction. Okay, let's say the current is coming from the top downward for the first one, Let's see how the video goes. Now in this case now, the current is coming from down upward for the two parallel conductors. When this happens, remember that they will generate magnetic field. When they generate magnetic field and they are parallel to each other, what is observed that there will be an attraction of the magnetic field as seen in the diagram. So when two current carrying conductors are in the same direction, their magnetic field attract each other. But when they're in the opposite direction, in this case, one current is coming down, the other one is going up, there will be repulsion. So there will be a repulsive force. The other one was the attractive force. This time around, there will be a repulsive force. They will repel each other as can be seen in this video. So this is the observation when you have two current carrying conductor in the same direction and in the opposite direction. The two of them in the same direction, the force of attraction exists. The two of them in opposite direction, the force of repulsion exists. Okay, having said that, shall we now talk about also taking a wire or a current carrying conductor through a magnet this time around? The previous ones we have said that when you connect electricity to a current carrying conductor, it generates magnetic field. But now another experiment is that we are going to be taking a current carrying conductor through the field of magnet as seen in this diagram. When you do that, what you observe is that by the time you take through that current carrying conductor through the magnetic field, the conductor will move in the direction of the force that is acting on it. And a scientist called Fleming proposed a rule concerning that. In this diagram, you can see this is the north pole of the magnet, this is the south pole, generating its magnetic field, as you can see, from north to south. Now, this is the conductor. Now, in Fleming's left-hand rule, it says that if the index finger is showing the magnetic field as seen in this diagram, this Fleming's right hand, the index finger is representing the magnetic field, which is letter B. Okay, and then the middle finger is representing the direction of the current. Then the direction of the motion of that conductor will be the direction of the force, provided that these three fingers are mutually perpendicular to each other. When I mean perpendicular, that means they are right angle to each other. So from his left hand rule, he is able to establish the directions of both the magnetic field, the current, and the direction of the conductor itself. Okay, so this is the rule. The rule states that if the thumb, the forefinger, and middle finger are held mutually at right angle to one another, that means perpendicular to one another, with the forefinger pointing in the direction of the magnetic field and the second finger in the direction of current, then the thumb will point in the direction of motion, that is, the direction at which the force will move the conductor. That is the force that acts on a current carrying conductor in a magnetic field. In a magnetic field. Alright, so having said that now, let's now talk about some of the area of application of this electromagnetic field. We are going to be looking at two major applications. Firstly, it can be applied in electric motor. You know, electric motor is the major motor we have in our electric fans or any mobile appliances. Now, the electric motor and the moving coil galvanometer, these two make use of electromagnetic field. Let's briefly talk about them in this topic. Now, for the electric motor actually is a device that converts electrical energy into mechanical energy. Like our fan that we use at home is actually electric motor that is making it to work. It converts electrical energy that comes from the source of electricity and then turn it to mechanical energy, which is a movement. Now, this is the diagram here. You could see the movement of this electric motor. This as a result of this magnet in it. This S and this N represent what? The horseshoe magnet, the south and the north pole. Now, by the time electricity enters the, the electric motor, based on the Fleming's right hand rule, okay, the force of the armature, that's the coil now, the direction of the coil is dependent on the force acting on it. And that force, we have already said, is perpendicular to the direction of the flow of current and also to the direction of the magnetic field. Okay, so this is able to be achieved. This is achievable because as a result of what? Of electromagnetic field. The second area of application of electromagnetic field is in moving coil galvanometer. A galvanometer is a device for detecting very, very small currents or sometimes potential difference. How does it work also? Like we have said, it makes do of the magnet and then a coil in the magnetic field. Now this is the north pole and this is the south pole of the magnet. Now, as the electricity enters into the coil that is in the magnetic field, it's being moved, the force acting on it moves this pointer, which point are the particular current that have entered into that into the galvanometer. So the motion of this pointer is as a result of the force that is acting on it. So these are the two areas of applications of electromagnetic field. Okay, and the last part I would like us to talk about is also the force that act on a moving charge in a magnetic field. When you put a charge in a magnetic field, for you to determine the force that act on that electric charge, okay, there's a formula that is F, which is the force, equals to the quantity of charge, which is Q, times the velocity of the charge, which is V, times the magnetic field strength, which is B. So this formula is saying that the more the magnetic field, the more the force that acts on that charge. Also, the more the velocity of the charge in the magnetic field, the more the force that is acting on it. All right. So these are the areas of interest in this topic. So I would like to draw the curtain here. So till I come your way again, thank you for listening. Bye for now.